Anyway, so here's the situation we've got. This is a little jumbled, but I'm going to need room on my paper, so here we go. We have a wire that is running from here across this direction, and the wire has a current in it of 100 amps. So that's our initial current is 100 amps and is flowing to our right as we look at this. Now, set up next to the wire, we have a rectangular loop of wire. And it's not part of this circuit, it's just in the general area, so it'll be influenced by the magnetic field of this current here. And obviously it's not to scale, but we're going to say that this loop is 4 meters long, that's 4 m, so 4 meters long, and 0.1 meters, so that's 10 centimeters high. So it's making a rectangle 4 meters long by 10 centimeters wide. And we're going to say that the center of that square loop, rectangular loop, is 0.2 meters from the wire itself. Okay? Now, in the loop, there is a single 2 ohm resistor. And the loop itself, I should put this in here, consists of 1,000 turns. So we have some very fine wire which is wrapped around and around and around and around 1,000 times, not connected to anything but itself. And at one point in there, there's a 2 ohm resistor. Now, in this problem, we're going to say that the current, which originally was 50 amps, that it's, for some reason, it's going to be reduced to 50 amps. And the time that it takes to make that change is 1/60th of a second. Excuse me. And what we're going to try to find is the energy that was dissipated by this resistor during that change. Okay, so first thing we have to think about here is, well, is there current running through this loop when the wire is just carrying 100 amps? So we just have steady state 100 amps. First thing we see is that the magnetic field which is running through this loop is coming toward us. So it's going to be the arrow points, it's going to be spots, it's coming toward us. How do we know that? Because we're going to use the right-hand rule for field. If this is the current with the pen, I grab it with my right hand, I point my thumb in the direction of the current, which is to the right as we look at it, and that means that the field lines come up on the top side of this wire. So the magnetic field produced by this current is coming through this loop toward us, up out of the paper toward us. Now, as long as that current is constant and unchanging, there will be no voltage, which means no current in this loop at all. Because as you recall, you get a voltage potential when there is a change in the magnetic flux. The voltage only exists while the flux is changing. So in a steady state condition, there is no current in this wire whatsoever. But when the current drops off to 50 amps, the current is cut in half, then there's going to be a voltage during that time that the current is changing. So that's what we're going to try to figure out. Okay, so how do we get from all this gobbledygook to energy dissipated by the resistor? So we're going to come up with some kind of intermediate steps that we can take here. So the energy dissipated, well, that depends on the power that is produced by this, or that exists, yeah, the power that's dissipated by the resistor there. So we're going to have to find the power on the way. Well, what does the power depend on? Well, the power depends on the voltage and on the current in the wire. So we want to figure out the voltage that's in there, and probably along the way, if we know the voltage and the resistance is given, we'll be able to figure out the current along the way. Maybe we want to know that, maybe we don't. Or maybe we need to know that, maybe we don't. Now, how do we figure out the voltage, which is the EMF, electromotive force in this wire? Well, that depends on the flux. So we're going to have to figure out the flux for this. And what does the flux depend on? The flux depends on the change of the magnetic field in that exists in that that loop. So we're going to have to figure out some magnetic fields here. If we can figure out the initial magnetic field and the final magnetic field, that will tell us the change in the flux. If we know the change in the flux, it'll tell us the voltage that exists in the loop. If we know the voltage and we know the resistance, we can figure out the power. And if we know the power, we can, and the time that the power existed, which is 1/60th of a second, then we can figure out the energy. Okay, so let's take it from the top. Step one. Step one, we are going to find the magnetic field. That's B. And the formula for finding the magnetic field around a wire like this is mu naught. That's the permeability of free space, I think, or permeability of vacuum, times the current, divided by 2 pi times r, where r is the radius or the distance from the wire to where we're interested in our magnetic field. Now, we are going to assume, since this is such a narrow slice, it's only 10 centimeters across, that the magnetic field is the same everywhere in this within this loop. Now, that's not exactly true. It's going to be a little bit weaker up here and a little bit stronger down here where it's closer to the wire, but we can say, just for the sake of discussion and argument, that it's going to average out to be the same amount everywhere, and that the average will be where it is at the center here. So we're going to pretend that the field is constant and our radius is 0.2 meters. Okay, plug in some numbers here. This comes out to be 1.26 times 10 to the minus 6th. That is the value of mu naught. This can also be 4 pi times 10 to the minus 7th, I think. So this is 1.26 times 10 to the minus 6th is the number. Our current is 100 amps divided by 2 times pi times the radius, which is 0.2 meters. All right? We run all that through the calculator and we wind up with 1.0 times 10 to the minus 4th Teslas. Okay, there's a couple, it's 1.00 and I think 2. There's a couple digits farther out, but we can round this off to 1.0 times 10 to the minus 4th Teslas. If you want to pause the video at this point so you can do that calculation, that's probably a good idea. But we figured out the strength of the magnetic field initially. All right, step 2, we're going to find the flux, which, as you recall, is basically the amount of magnetic flow, if you will, that is coming through that opening. So step 2, we're going to find the flux. And flux is this cool looking symbol right there, and we find it by B, the magnetic field, times cosine theta times the area of the opening that we are interested in. Now in this case, what are we going to use for the angle? Well, we've said that the loop is perpendicular to the wire here, so I guess we should do like a side view. So if this is the wire, and it is actually, you know what, I'll do it here. Okay, this is the current carrying wire coming straight toward us as a dot. And that means that this rectangular loop is arranged like this. Now, if the current is coming out of the table toward us, we use our right-hand rule for field. That means that the magnetic field is running this direction, like so. And it is perpendicular to the flux at the point where we're interested in it. So this angle, cosine theta, is going to come out to be 1. Okay? We're not putting this at any funky angle or offset or anything like that where we have to worry about this. So cosine theta will turn out to be 1. So we have our magnetic field 1.0 times 10 to the minus 4th Teslas times 1, because that's the cosine theta, times the area, which is 4 meters, times 0.1 meters, comes out to be 0.4 square meters. We multiply all that out, and we get 4 times 10 to the minus 5th Webers. Again, if you want to pause the video and run that calculation, go for it. But that is the flux that is coming through our loop when there's 100 amps running through the wire. But this problem says we're going to reduce the current to only 50 amps. So if we reduce the current, on this equation up here, we're going to go from 100 amps to 50 amps, which means we're going to have half as much magnetic field, half as strong a magnetic field. So B is going to be half as big, which means we're going to have half as many Webers. Okay? So if we cut it to 50 amps, then the flux is going to be 2 times 10 to the minus 5th Webers. Okay? Which, since it's cutting in half, that is the change in flux. Okay? We have half as much as we did before. That means we lost half of it, so 2 times 10 to the minus 5th Webers, that is our change in flux. Okay, step 3. Now we need to find the EMF, the voltage, as it were. And for that we use Faraday's law, which is the change in flux divided by the change in time. We've done the hard part. So the change in flux is 2 times 10 to the minus 5th Webers divided by 1/60th of a second. So to do that, we can just multiply the 2 times 10 to the minus 5th, multiply that times 60, and we wind up with 0.00120 volts. That's how much EMF, that's how much voltage there is in one loop of the wire. Not very much, but it's not a very huge area. It's not a very strong magnetic field, so what do you expect? However, we have 1,000 turns of wire. So in a single turn of wire, this is the voltage we're going to get, 12 1,000ths of a volt. Not very much. But since all the loops are in series with each other and each loop is getting this much of a push, that means if we multiply this by 1,000 times 1,000 turns, we're going to wind up with 1.2 volts. 1.2 volts. That's the voltage that we're going to get in this coil up here. Okay, so now we need to find the power. We found the magnetic field first, we found the flux, we just found the voltage or the EMF. Now we're going to find the power. Okay? Power is equal to V squared over R. That's one of those handy shortcut equations that we had. If you don't remember that one, how do we get it? Okay, well, P equals IV. That's the power equation. Hopefully you remember that. And V is equal to IR, our old friend Ohm's law. So V equals IR, that means that I is equal to V over R, and we can substitute V over R in here for I. So we get P is equal to V over R times V, which is V squared over R. Right? I'm showing you that derivation for review here because P equals V squared over R, that's not on the AP gouge. The other ones that's useful is P equals I squared R. Okay? So if you know the current and the resistance but you don't know the voltage, you can figure out the power with this shortcut. If you know the voltage and the resistance but you don't know the current, you can use this shortcut and you get where you're going with it. Anyway, so this is the one we have because we don't know the current. Turns out we don't need to. So the voltage is 1.2 volts. We're going to square that. We're going to divide it by the resistance that exists in that circuit, which is 2 ohms. And we wind up with 0.72 watts. 0.72 watts. Fantastic. Okay, now what's a watt? A watt is 0.72. A watt is the rate of doing work, or the rate of releasing energy, and it's in joules per second. So we have 0.72 joules per second, and we multiply that by 1/60th of a second. And so we wind up with 0.12 joules. Ain't that grand? So that's how much energy the resistor dissipates during this change in current.